Comrades, welcome to the second half. We're over the hump. The term is 11 weeks long, but the length of the material is just 10 weeks, and this is the start of week 6. After much delay, we're finally coming back to proofs. Ask has received a serious upgrade that took Connor about 2 weeks of hacking. So the plan for this week's explorations is, in this video, I'm going to show you what it looks like to prove simple equations between programs by example. Then in the next video, I'm going to dive into a bit more detail about what's actually happening internally in Ask, which should hopefully help you to avoid being very confused. And then in Exploration 3, I will show you how to do proof by induction, which we need to prove almost anything at all that's interesting. Then next week, you'll get a lot more practice at writing proofs by induction, and I'll also introduce some more advanced proof techniques that we can use to prove more things. Okay, let's get started. So if you think back to the first couple of weeks, what could I write after I write prove? Well, I can write things which are built from propositional variables and logical connectives. So I could say, for example, P implies P. Proof P implies P. So P here is a propositional variable, and implies is a way of building new propositions from smaller ones. So I'm going to introduce a new way, a new type of thing that you can try to prove. So here's a data type. This is the natural numbers. So a natural number is either 0 or the successor of a natural number. I can now write, for example, prove 0 equals 0. So this is now asking me to prove that two pieces of data are equal to each other, namely that 0 equals itself. And because we have a new way of asking questions, we also have correspondingly a new way of answering the question. So we have a new method of building proofs, which is called tested. So I can say prove z equals z tested. And what happens is that ask tests that z does actually equal z, and then it accepts this as a proof. So what happens when I send this line to ask is that it tries to simplify both sides of the equation. And in general, simplifying one side of an equation will involve running programs. So in this case, there's nothing to do because z is already fully simplified. So this might look like a massive disappointment, but let's try to upgrade one step higher. So here we have plus. This is a program. So this is the addition function on natural numbers. So now I can write, for example, prove that 2 plus 2 equals 4. And I've miscounted my brackets. And now I can again say tested, because ask will run this program 2 plus 2 and check that the answer equals 4. This also works the other way round. So I can put this here. And this is also an accepted proof. I could also, for example, prove that 1 plus 3 equals 2. 1 plus 3 equals 2 plus 2. So here, ask is running the programs on both sides of the equation and checking that the results are the same. Okay, this is still a little bit boring. A slightly more interesting thing that we might want to prove is to prove that 0 plus anything equals itself. So this is now an equation that involves a program, namely plus, but it also involves an unknown input n. So although this sounds boring, this equation is actually telling you an infinite number of things about what this program will do on an unknown input. And it turns out that we can just write tested again, and this is enough to complete the proof. So let me explain what's happening here. So ask goes to the definition that we wrote for plus, and it knows that the first input is 0. So it knows that when we say from first input, it knows that the first line runs. And because of this, even though the second input is unknown, it knows that it equals itself. Okay. But there's a big catch, which is if I try to prove something equally obvious, like n plus z equals n, so it's the same equation, but with the inputs are plus the other way round, this doesn't work. So ask accepts it, but it asks us to prove the same thing again. What's happening here is we actually need proof by induction to prove this. And this is a consequence of the fact that we've defined plus this way round with from on the first variable. So if we had chosen to define plus the other way round, which is also possible, then this proof would be easy and the first proof would need a proof by induction. Okay, let's do another example that's very similar. So here's the data type for lists. Const A, infix R for cons, and then I can say, here's the concatenation function on lists, which I showed you in one of the earlier explorations. Say x is cons, x is concatenate y's, define inductively x's, where define from x's, and then this case is y's and the head cons. Tail case is head cons tail concatenate y's. Yes, let's get rid of this. And now I could write, for example, prove empty list concatenate x's is x's tested. And again, ask will accept this proof for basically the same reason that it tries to run the concatenate function. It knows that the first input is empty, so it knows that this case runs. On the other hand, if I try to prove something else equally obvious, like empty concatenate x's is x's, this will not work. Sorry, this is not what I mean. There we go. This is the one that doesn't work. For the same reason as we had with plus, that we need to use proof by induction on x's for this. And here x, so this is proof by induction on a list rather than a natural number. Okay, so in the next video, I will continue telling you about this and go into a little bit more detail about what's happening.